Good evening, everybody. It's 7:30, so I think we will get the party started tonight. For those of you who don't know me, I'm not Bernie, just in case you were wondering. My name is Sue McLaughlin, and I'm second chair. Bernie has been under the weather all this week, and he is unable to be here with us tonight. So one of the duties of the second chair is to step in and take over the reins to run the meeting. And I have to be honest, I wasn't nervous until about 10 seconds ago when Chris said, "We're ready to go." So now I'm up here shaking and I'm thinking, oh my God, what am I doing? Bernie's not here, and that means that we have a fill-in guest speaker, but he's not really a fill-in because he is an integral member of the club. John Gauvreau will be filling in for Bernie with an awesome talk tonight. And Chris has made some modifications to our Facebook and Zoom feed tonight. So tonight, I think we can actually say hi to everybody out in Zoom land, and they're going to say hi back.
Hello, Zoom people.
Hello from Zoom land.
Unmute.
Hello.
Hello.
Hello,
Hi.
Matt.
Hi, everyone.
Okay, good, Susan.
All us Zoomies saying hello.
Hello. Okay, you guys are taking up too much airtime. I'm shutting you off.
So hi, everybody out there in Zoom land. And hopefully the video in Zoom land is also good tonight because Chris has made some modifications for that as well. And that's why we have the lights on up here so that I'm not a black shadow out in Zoom land and in Facebook. So welcome to all of our friends who are out there online tonight from near and far away. So let me see. This is our agenda for tonight. It's been up here for a while, so I think I will move on. I want to start off by saying thank you, first of all, to everyone who brought treats last month to our December Cold Moon Social. It was an awesome evening. There was tons of conversation, tons of laughter, reliving some interesting, observing events from the summer. Chris, we're getting a little bit of feedback. Okay, we're good. So I want to say a special thank you to everybody who brought in treats, homemade or bought, and it didn't really matter. Not much was left at the end of the night. I also want to say thank you to the people who have volunteered to be greeters at the door. Tonight we have Reed McNaughton with us, along with Chris and Dan and Robert Smoke. They are hanging out there at the back. So thank you to all the people who have volunteered to do that. And again, calendar sales. Our calendar sales went really well. We have a few calendars left that we are selling tonight at a discount price of $10. So if you want to pick up a second one, you can. But thank you to everyone who picked up calendars. And again, thank you to Doug for doing an awesome job with putting all of that together. All right. I'm working tonight from some slides that I've put in and some slides that Bernie has made, so it's kind of a hybrid tonight. And just for do we have any new people here? Oh, John, you're not new. Steve, you're not new. Welcome. Welcome. And I know we have some people who haven't been out to a live meeting in a while, so welcome back to those people as well. And just a reminder of some of the things that our club does. Our observing programs, the event horizon, the Lunar Scope program, the library, our dark sky observing site, all the public outreach that we're going to start doing again now that we're kind of over the hump with COVID. All the education presentations that we do for various groups in and around the area, our presence on social media, and I think the best thing of all is the networking that we get to do with others who share our passion for the night sky and share our passion for astronomy, all aspects of astronomy. I'll get there. Don't worry. Our Lunar Scope program, I was going to have Paula speak to that tonight, but unfortunately she is not here. And I know there have been a couple of questions about membership as well. Paula is not with us tonight. If you want to renew your membership because they run out at the end of January and you are taken off the list. So please pay before the end of January. You can do it online on the website, and your membership card will be mailed to you, or you can arrange to pick it up at the February meeting. Any questions about membership? Okay. Denise has got the library open and running at the back. There has been a large donation from the late Michael Jefferson's estate of library books. And I'm guessing that there's probably easily around 200 books that have been donated. They will eventually be processed and will end up in the library and also end up as door prizes. So we're very grateful to Michael's estate for providing us with those materials of a very, very extensive library and very well curated as well that we can take advantage of. So thank you to the family for that. And Denise is back there. She's got lots of interesting things to look at, so visit her during the break. And if anybody has an overdue book, well, she'll eventually find you. I checked tonight. We've got some nice food share donations in the bin and also some money, so thank you for that as well. That is definitely appreciated by Hamilton Food Share when it is dropped off. And just a reminder that, you know, they can buy twice as much with the cash that we give them that we could do in buying groceries for them. So the cash is just as valuable as the food goods. All right, our upcoming events. Jim, Astro 101 is right on the top. Astro 101 is our beginning astronomers group, and it's going to start meeting the end of January, early February, and it meets on Zoom. And it covers many, many topics that people who are new to the hobby want to learn about. Everything from what transparency is to the type of eyepieces you can use, to the type of telescope you should buy or not buy, to how you plan observing sessions, to what you start with, to binocular viewing, to astrophotography. It covers many, many different topics. Sometimes the topics are raised by the participants, and then John Gauvreau, who coordinates that program, gathers the speakers, and there's usually a different speaker each week that specializes in one of the topics they're interested in. I have sat in on this group quite a number of times, and every time I've come away learning something new. So it isn't just for people who are new. There are always interesting discussions and things that come up. So if you are interested, John is actually here tonight. He's sitting there at the back. He'll be up here later. And please speak to him if you are interested. And his contact email is up there. February, we have Laura Park. Oh my goodness. I bought. Let me tell you, it's been one crazy week for me. This is not the job I usually do, so it's been kind of a crazy week. I apologize for that. I went through it, and you know, after a while, after looking at it, you don't see the mistakes anymore. In February, our speaker is Laura Parker on the 10th, and then on the 18th, we're going to have a Saturday telescope clinic that will be here. I'll speak more about that in a moment. And on March 10th, our speaker is Carrie-Ann Hepburn, who is an amazing astrophotographer. Yes. Oh, yes, definitely. Yeah, the Astro 101 is free. There is no cost. All right, so as long as you remember, it is definitely free. So the telescope clinic, Matthew Mannering is going to be coordinating the telescope clinic. We did this in the past before COVID. There was a picture, I think, that John Gauvreau took of our previous location, the Hamilton Spectator Building, of a telescope clinic, and that's kind of what it will look like. We're going to have stations at this clinic. There'll be greeters at the door, just like we have at our general meeting. Then we'll have a Dobsonian and Newtonian reflector station, a Schmidt-Cassegrain Maxikov station, a refractor station, solar station, and then a technical assistance station. And what we are looking for is we're looking for some volunteers to come out and help with that. So it's about a 3 to 4 hour time commitment in the afternoon. We have to confirm the time with Mac here, but I think it'll run, the public session will run from 2 to 4, and then we'll have the room from like 1 to 5 so that we can set up and take down. We'll need people to greet at the door. We'll need people with different types of telescopes. And no, you don't have to have a Mac, a Schmidt-Cassegrain, a Dobsonian, a refractor. You don't have to have all of those, just one. If you'd be willing to come and set it up at the appropriate station and be able to answer questions from members and also from the public about your telescopes. We're also looking for people who would come and not necessarily bring a telescope, but would be able to assist people to set up their new telescope that they may have gotten for Christmas. We've had that question quite often, and give them a little few pointers to get going. And then to provide some technical guidance and assistance. My telescope mount isn't tracking anymore. What am I doing wrong, or what's wrong with it? So we're looking for people who might be interested in helping out for a commitment for that afternoon. Matthew will have a sign-up sheet at the break, and he will answer any questions that you have with any of the details of that day. So Matt is sitting up here, and there he is, and you can ask him. And if you are online and would like to help out with that, you can email secondchair@amateurastronomy.org, and you will get me, and I will forward that to Matthew. So if you're interested and you're online, please don't feel you can't, but if you'd like to. And if you don't want to volunteer, you can always just come and hang out and ooh and ah at other people's telescopes. Are there any questions about this event? Oh, great. Okay, moving right along. The elephant in the room. This tonight we're going to have John Gauvreau, who, as I said earlier, is a long time member of this organization. He has served in many different capacities. He has taught astronomy courses both at Mohawk and at Conestoga. He is an excellent public speaker, and I turn the floor over to John.
And thank you, Sue, very much. Again, touching interest in Astro 101, I really like the misspelled Astro 101 with a sure astronomy. I'm trying really hard not to take it personally, but you can't argue with the facts, you know, so. Okay, there you go. So, okay, great. Excellent. Thank you. Thank you very much. That's wonderful. So I wasn't supposed to be here today. I'm jumping in at the last minute because Bernie's a little under the weather, and I really hope that Bernie feels better soon. Is Bernie zooming in with us? So get well soon, Bernie. So I put this together in a couple of days, those days being yesterday and today. And that was while I was working as well. So it really isn't what I wanted it to be. I actually wanted to cover more, and I wanted to be a little more comprehensive. So this is kind of about half of what I wanted to cover, but it's the first half because then it was time to come here, and here I am. So maybe at some point in the future there'll be a part 2, and I'll finish this, finish this talk another time. The title of the talk is "The Elephant in the Room: Studying the Star on Our Doorstep," and it's about the sun. As amateur astronomers, we all spend so much of our time searching out the faint fuzzies, as we call them, looking for the faintest stars and the most remote galaxies. But why do we ignore the elephant in the room? There's a star right on our doorstep, and not only does it give us the opportunity to study the workings of a star up close, it also gives us, as amateurs, the chance to see a star up close. How does one ignore a star? How does one ignore the sun sitting right there? Like always, I always like to have a little bit of history in my talks. Those of you that know me know that you're always going to get a little dose of history. So how about this? All right. Ra, Sol, Surya, Hinti, Hinichahu, Mithra, the Egyptian, Norse, Hindu, Aztec, Mayan, and Persian gods of the sun. Just some names from a very long list. Clearly, and not at all surprisingly, the sun has held a very special place in the mythology of many civilizations. And why wouldn't it? Dazzlingly bright, powerful, and mysterious, hanging over our heads all our lives. Here are a couple more that you will recognize. Right? This is Sol, and we'll follow it with Helios, the Greek and Roman names for their sun gods. All right, other way around, Roman and Greek names for their sun gods. We know these names well. The Greek Helios, from which we get heliosphere, helioscope, heliopause. And because this element was discovered on the sun before it was discovered here on Earth, helium is named for Helios. And then, of course, the Roman god Sol. And it is from this name that we derive the word solar, as in solar power, solar eclipse, the solar system. We're very used to using sol to mean something having to do with the sun. But don't look down on these ancient peoples because of their reverence for the gods. Don't think that we are without such reverence for the ancient gods of the sky. We modern-day people are just as bad, quite frankly. This week started with the Moon's Day on Monday. And then we celebrated the Norse gods Tyr, Woden, and Thor with Tuesday, Woden's Day, and Thor's Day. Actually, Woden's Day is why Wednesday is spelled with a silent D right in the middle of the word. And then, of course, today, Friday, is named for the goddess Frigg. Tomorrow is Saturn's Day. The beginning of our weekend is Saturn's Day. And, of course, we finish the week with the Sun's Day. We still do it now. Every week, we finish our weekend with a celebration of the sun, Sun's Day. All right? So there we go. I always have to throw in a little bit of stuff like that. But what about actual observations of the sun, all right, through history? Going back to 800 BC, the Chinese Book of Changes mentions the darkening on the sun, and elsewhere they mention an obscuration on the sun, not of the sun, but on the sun. These are probably naked eye observations of sunspots. The Greek academician Theophrastus, he was a student and later the successor of Aristotle in 300 BC, said that he saw a large spot on the sun that was visible for 8 days. Now this is 500 years after the Chinese Book of Changes, and good for him, that's great. By this point, the Chinese records were regularly recording sunspots. If we jump ahead quite a bit of time, Leo Diaconus in 968 AD, from what he was from what would be today modern Turkey. All right. He wrote the following. I'm going to quote him directly. He wrote the following. At the fourth hour of the day, darkness covered the earth, and all the brightest stars shone forth. You know what's going on here, right? Of course. It's an eclipse. It was possible to see the disk of the sun, dull and unlit. No, that's the moon, but it's okay. It was possible to see the disk of the sun, dull and unlit, and a dim and feeble glow like a narrow band shining in a circle around the edge of the disk. What's he seeing there? Right? So he's seeing either the corona or the chromosphere of the sun. In 1128, John Gauvreau described a sunspot in this way. In the third year of Lothar, the Emperor of the Romans, the 28th year of King Henry of the English, Saturday, the 8th of December, there appeared from the morning right up to the evening 2 black spots against the sun. And, there's his corona. And there actually is a drawing from describing that very thing. And of course, that's I've seen better sunspot drawings, but I think that's not bad for almost 1,000 years ago. And of course, this type of thing is exactly what they're looking at. And not long after that, 1185, in the Russian Chronicles of Novgorod, it says this: in the evening there was an eclipse of the sun. It was getting very gloomy, and stars were seen. The sun became similar in appearance to the moon, and from its horns came out something like live embers. These are prominences rising up from the surface of the sun that's visible there. So there you have it: sunspots, solar prominences, the corona, the chromosphere, all observed long ago, although they mostly didn't understand what it was. There we go, that's it there. What it was that they were looking at. So what were they looking at? What is the sun? Right? The sun, of course, is the source of all our light and all the heat that we enjoy. Provides the light that we need to see, keeps our planet temperate, it keeps the water liquid, provides the energy for the plants and animals to survive, and that includes us, of course. What is that source of energy? What is actually going on in there? Well, of course, we know that the sun is a star up close, and the stars are suns far away. We know that the sun is made mostly of hydrogen and helium, and that a nuclear fusion reaction in its core is the source of its power. So, how does that work? To understand, let's look at the sun from the inside out. Now, as I said, we know that it's made mostly of hydrogen, okay, having formed out of a nebula some 5 billion years ago. Once formed, the sun was structured into different layers. And for the vast majority of the sun's life, okay, the sun will be structured in a manner very similar to this. All of the images that are in this talk today are used with permission, are in the public domain, or are my own. So there's everything here is permissible. So let's have a quick look at that structure. There's, depending on how you want to count it, 6, 7, or 8 layers to the sun. There's, I think they list 7 here. The core, the radiation zone, the convection zone, the photosphere, the chromosphere, a transition zone, and the corona. There's 2 transition zones. There's another transition zone lower down, and you can either count 1 or both of those, and if you do or don't, well, then there's 6 main different layers and a couple of transition zones. The very core of the sun, of course, is where all of the energy is produced. It's very high temperature because the gases are compressed. And as you compress gas, it will heat up. So think of a bicycle pump like this, right? And as you compress the gas, all right, even the air inside a bicycle pump will start to heat up. Who wants to be part of the experiment here? Who's going to pump the bicycle pump for me? Come on, somebody. Yes. I'll come to you. Fantastic, thank you. All right, so Reed comes to the rescue. That's awesome. So he's going to sit there and pump the bicycle pump, and as the gas in the sun is compressed towards the core, it rises in temperature. The core of the sun gets up to 15 million degrees. When you hit 15 million degrees, you let us know. Okay, so Celsius, Fahrenheit, Kelvin, well, it's kelvins, but who really cares? Because, it's 15 million. It's incredibly hot, all right, when you get there. At 15 million degrees is hot enough to maintain a hydrogen nuclear fusion reaction. Hydrogen fuses together to form helium. Now, most of you know this, but most people, of course, simply think that hydrogen has one proton and one electron. Helium has two. You take two hydrogens, you put them together, you have all the ingredients you need to build a helium atom, and that's all there is to it. But it isn't. It's a very complex process, okay? And the complex process involves, it's called, the primary method is called the proton-proton chain. And we're going to have a look at that. And it actually involves getting protons close enough together to fuse. But the result produces not just a simple helium atom, but you will get, let's press the right button. You get a variety of other products that come out of it. And here's a look at how the process works here, okay? Now, this isn't a physics class, and I am no expert, believe me, okay? So I am going to generalize some things here, but just to give you an idea of what's actually going on in there. All right, so you start with a proton and another proton. So that's great, two hydrogen atoms, two protons, and you smash them together. Now, if the sun weren't that hot, okay, they wouldn't be moving that fast. And if they weren't moving that fast, then because they have the same charge, they both have a positive charge, they'd repel each other and they wouldn't fuse. But because it's so hot and they're moving so rapidly, they crash into each other before they can put the brakes on, and you have this collision. And this collision results in something called a deuteron, which has one proton and a neutron, and where'd the extra charge go? It went off here in the form of a positron. What's a positron? It's just like an electron, but it has the opposite charge, a positive charge. It goes off and finds an electron. The positron and the electron meet each other. They're opposites. They destroy each other and are converted to energy. And off goes shooting a gamma ray. And gamma rays come pouring out of the sun, the core of the sun. Fantastic. That's great. So what happens to what we had left? Well, this deuteron finds another proton, merges together. All right. And that produces helium-3, because now you've got two protons in there, and that's what you need for helium. And so now you have helium-3, but helium-3 isn't stable, so that's not going to work. So what you need to do is you need to do the whole thing all over again next door. You need two protons, merge them together, fuse them together, produce a deuteron, produce a positron that meets an electron that produces gamma rays, and then that new deuteron meets another proton, produces another helium-3, and then that finally finds its way and meets the first helium-3. Those two merge together, to produce helium-4, and you've got 4 protons in there and 2 neutrons, and that's more than you need for helium. You only need 2 of those protons and 2 of the neutrons. So the 2 extra protons go flying off into somewhere in the sun. And that's a good thing, because you need that, because, look, I didn't need just 2 of these hydrogen protons to fuse together to make helium. I needed 1, 2, 3, 4, 5, 6 to make the whole thing work. So having some extra protons flying around is a good thing, because they are going to go and find another one and start this all over again, start the chain all over again. And that's what makes it the proton-proton chain, all right, because that cycles back and starts all over again. Now, you may notice up there that there's one other byproduct of this, and that's this little guy right here. A neutrino comes pouring out of there. And this neutrino coming out of there is what makes the sun the biggest producer of neutrinos around. The sun may not be shining on us right now. It's nighttime here. But I assure you, there are millions, billions, trillions of neutrinos from the sun pouring through this room right now. Just as this window is invisible, is transparent to regular light, the walls are transparent to neutrinos, the floor is transparent to neutrinos, the entire Earth is transparent to neutrinos, and even though the sun's down there, those neutrinos are pouring up right through the Earth, right through this room, and right through you right now. And it's no problem. So, lucky break for us. How you doing there? So your hands are really hot. Okay, let's take that as proof that it works. So now give the bicycle pump to somebody. Feel the bicycle pump. Can you actually feel that it has heated up? Yeah, that's because you're compressing the gas inside. So just pumping a bicycle pump, compressing the air in the bicycle pump will heat up the air in the bicycle pump. Think about the gravity of the sun compressing the gas of the sun and how much it heats it up. Heats it up to 15 million degrees in the core, and that's enough to do this right here. So now, before we leave, of course, we'll point out that we went through all of this process, okay, for one thing, and that's these gamma rays right here. These gamma rays that come shooting out, those gamma rays are the power that's coming from the sun. Those photons are what are pouring out of the sun, okay, and providing all of the light and heat that we experience here on the Earth. We're not being bombarded by gamma rays. They go through other issues before that they get to us, and we'll talk about that. But there's our source of energy right there, those gamma rays. So, and all you have to do is convert the hydrogen and the helium to get that. So this is a tremendous amount of power. And so, but I want to point out that that power is part of a very delicate arrangement that we have on the sun. The sun is powerful, but also delicate, all right? This heat is coming, is there in the core because of the compressed gas. And it's compressed because of the tremendous gravity of the sun. The sun itself is something like 300,000 times more massive than the Earth. That's a lot of mass, and that means a lot of gravity, and that gravity wants to crush the sun, collapse it right down. But the heat inside wants to expand the gas, and that pressure from within is pushing back out. The sun is engaged in this wonderful, delicate balancing act between wanting to crush itself and blow itself up at the same time. And amazingly, these two forces balance in this delicate fashion, and the sun just sits there. It just sits there incredibly stable. And it will do that for 10 billion years. It's been doing it for 5 billion. It'll do it for 10. Not all stars are so delicately balanced. Sometimes, with some of them, gravity starts to win, and with others, the pressure from within starts to win. And some of them never reach that stability that our sun has, and they waver back and forth between the gravity winning for a bit, and then the pressure fights back, and then the gravity collapses it down, and the pressure fights back, and then they oscillate back and forth, back and forth. These are variable stars. They vary in brightness and temperature, and you can observe that out there. You can see some of these stars. Our sun, fortunately, is very, very stable. So now the sun shines on us, right? Almost. We're almost there. The energy has to get from the core of the sun, all right, up to the surface of the sun. And it has to go through all those other layers to get there. The first layer that it comes to is called the radiation zone. And don't worry, we're not going to spend this much time on each of these layers, okay? The first layer it comes to is the radiation zone. And now, this is really amazing. The core of the sun, with all of that tremendous pressure and density, okay, is actually transparent to these photons. They just zoom right out of the core, quick as can be. But the radiation zone is not. The radiation zone is opaque, okay, to these, it's a slightly lower temperature, and it's opaque to these photons. So as these photons, these gamma rays that have just newly formed, and they're like, yes, out of here, zoom out of the core of the sun, and then they come to the radiation zone, and it's like hitting a brick wall, all right? They just slam into the gases there, all right? And they hit an atom, and the energy from this photon pours into an atom, a hydrogen atom, in the radiation zone. That atom is energized, and it says, okay, that was fun. Now I'm releasing the energy, and off you go. And it goes all the way to the next atom and smashes into it and goes through the same process, and then goes to the next atom and goes through the same process and goes to the next atom. And this energy works its way from the core of the sun up through the radiation zone, which represents about half the size of the sun, and works its way through atom by atom. And that's an incredibly slow process. So this radiation, these photons that want to zoom off at the speed of light and are newly formed in the core of the sun, take about, on average, 171,000 years to work their way from the core of the sun up through the radiation zone, all right? It's a slow process, all right? So the light that shines down on you, okay, the light that's shining down on you started out in the core of the sun over 170,000 years ago. As it does this, it's slowly transformed from very high energy photons like gamma rays and X-rays down to many, many low energy photons like visible light and heat. And that's a good thing for us because that saves us from being bombarded by these very dangerous high energy photons. When it does escape the radiation zone, it passes into the convection zone. And the convection zone, let's make the magic happen here. There we go. The convection zone works exactly like a pot of boiling water, okay, on your stove. The hot gases are heated by from the radiation zone beneath it. And as they heat up, they rise to the surface. They release that energy, they get cool, and it sinks back down, and it's just like watching a pot of water boil. It really is just like that. Looking at the top of the convection zone, you can see each of these sections here is a convection cell, hot in the middle, and the gas bubbles up in the middle there, moves to the side, and falls back down in these dark crevices in between each convection cell. And this is a real image of the surface of the sun. This is a real image. I didn't take it, but it is, in fact, a real image. All right. And here at the top of these convection cells, we meet the photosphere, the next layer, the photosphere. And this is a term that you're probably very familiar with. The photosphere, of course, is two words put together. Photo, which means light, like photograph means writing with light, and a sphere, which is a ball. So the photosphere is the ball of light. Do I have a picture? Oh, yeah, okay, terrific, good. Yeah, I don't know the slides because I literally just put them together a few hours ago. Okay, so we're up here to the photosphere now. And the photosphere, the ball of light, is what you see when you look at the sun. Okay, this is what you see. This is what looks like the surface of the sun to you. And this is where all of that light is finally released to come flying out towards us here. Now, the amazing thing is when we look at the sun and we see that surface of the sun, it very much looks like a surface, right? I mean, look at that. I can see the surface. Absolutely. There's the top of those convection cells. I can see the surface. Now, we understand that it's not a solid surface, of course, but I want to impress on you just how tenuous it is. The gases there are very, very thin, and there's no real sense of differentiation from one layer to the other. As the gas thins, it eventually reaches a point where the photons can be freely released and they go flying off into space. And that's what we see as the surface. But if you were actually there in terms of the density of the gas, you'd never notice any change. It's a very, very gradual change, gradual change, gradual change. And at one point, it passes a threshold where it releases that energy freely. But if you were just measuring the density of the gas, you wouldn't even notice the change. The surface of the sun, or the idea that the sun has a surface, is very much an illusion. Okay, it's very much an illusion. So it passes up through the photosphere, and above the photosphere is the chromosphere. And the chromosphere means chromo and sphere, meaning color and a ball. So the chromosphere is the ball of color. And we call it that because when in an eclipse, we can see those prominences. Picture, photosphere, very solid surface, chromosphere. And during an eclipse, we can get to see the chromosphere. We can see the prominences of gas shooting up off the surface. And this is we see the vivid color of the prominences. We see how red they are. We see how vividly vibrant red this layer is. And that's why it's called the ball of color, the chromosphere, because of that. This loop gets annoying after a minute. So let's move on. And let's move on to the top layer, of course, which is the corona. And the corona sits above the very, very thin photosphere and chromosphere, and it stretches out far, far, far from the sun. This is basically what we refer to as the sun's atmosphere. But of course, as I said, there isn't really a solid surface and then air above it the way we have here on Earth. It's a very, very gradual transition as the gas thins and thins and thins. Corona means crown, all right? And you can see why, all right? This is the crown that sits on the sun. So there we go. So there's a bit about the structure of the sun. Now, many of you know that the sun goes, but I'll mention it anyways, the sun goes through an 11-year solar cycle, during which time it varies between very active and very quiet times. This is very obvious by looking at sunspot numbers. And over time, you can see the years at the bottom here, 1920s, 30s, 40s, 50s, 60s, and so on, right up to 2020 right there. And we're now moving into 2023, which is over about here. And this is counting sunspot numbers. And you can see how the number of sunspots rise to very high numbers and then basically drop to very close to zero. And up and down, up and down, up and down. This 11-year sunspot cycle has been known for hundreds and hundreds of years, and we have very accurate records of sunspot numbers for the past couple of 100 years. We have recently come out of a dip over here that is referred to as sunspot minimum. And you can see that it dipped right down to zero there. This was a very deep sunspot minimum that we've just been through. The sun has been very, very quiet. The solar observers have been very, very sad. But look, yay! Okay, it's on the upswing. It's on the upswing. Now, initially, for solar observers out there, I'm looking at you, Denise, initially, because we came out of such a deep, deep solar minimum, the fear was that this was going to be a rather shallow solar maximum. You can see not all maximums are created equal. Some are just okay, and some are awesome, and some are just okay, and some are awesome. But from awesome, it's been getting not as good, pretty lame, and the fears were that this one coming up were going to be really, really poor, the poorest we'd had on record. And yet, the sun is offering us a pleasant surprise. As we ramp up towards the next solar maximum, it's proving to be much more active than we expected it to be. And over the next 4 years, or the next few years, we can anticipate a really active sun with really, really good solar observing. Now, an active sun means other things as well. An active sun does interact with the Earth, It can provide good things like northern lights and bad things like power outages and satellite failures. You take the good and the bad with this. Right? For solar observers, the difference between solar minimum and solar maximum is in visible light, looking at the photosphere, seeing a sun at minimum, like the one on the left, and at maximum, like the one on the right. You can see the appeal of solar maximum. And for those people that have specialized telescopes that can observe the chromosphere, it's the difference between seeing the sun like the one on the left and the sun like the one on the right. It's a big, big difference, all right, between the two. So, speaking of how the sun looks, how does the sun look? All right. Sun watchers have a variety of ways to observe the sun. Fellow member Kevin Sawich, who is here tonight, gave an excellent talk on solar observing a few years ago, presented it in a video, and it's available on video, and I think we still have it available somewhere, and it's quite excellent. I'm not going to repeat him here, and I also didn't, as I said, I kind of ran out of time at this point and didn't really get to spend as much time on solar observing as I wanted to. But I'm going to start by saying the single most important thing that I can, and I cannot emphasize this enough. It is extremely dangerous to look at the sun with your eye or any kind of optical aid unless you are properly equipped and trained to use proper solar filters. Do not mess around with this, okay? People end up with permanent eye damage and blindness. Do not risk that without knowing what you are doing, all right? But when done properly, observing the sun can show remarkable things. So I took a series of images off of the Solar Dynamic Observatory to see what the sun looks like in a variety of different frequencies. And these images show us the sun today, all right? This is the sun today. There's the timestamp down below right there, okay? 2023-01-13, January 13th. These are today in visible light, and then we move through the spectrum to see it in a variety of different frequencies. All of this is showing us activity that is going on the sun today. This is just a few hours ago, all right? Just a few hours ago, around, it was around, there, actually, you can tell. This one was 3:30 this afternoon, all right? 3:30 this afternoon. I'm going to backtrack just, I'm going to steal just another minute, okay? I'm almost done. I'm going to steal just another minute here and backtrack just a bit. This here shows us what's called a hydrogen alpha view of the sun. And as the energy comes pouring out of the photosphere and into the chromosphere, all right, the density of the gas in the photosphere is just dense enough to absorb the energy and then re-release it. And in absorbing it, if we observe the sun, the spectrum of the sun, we see absorption lines. In the chromosphere, it's thin enough, okay, that it doesn't absorb that way, and it emits emission lines. And by filtering a telescope so that it observes only a very specific emission line coming from the chromosphere, you can use that telescope to look at the sun, and you don't see any of the light from the photosphere. All of that blinding white light from the photosphere is blocked, and you see only the chromosphere that shows you all kinds of activity, filaments and plagias and flares and prominences, all the things that I or somebody will talk to you about in another talk. So the last thing, though, that's worth mentioning before we pack this up here, of course, is eclipses. And it's very worthwhile talking about the sun lots over the next 15 months, because 15 months from now, on April the 8th, 2024, there is going to be a total solar eclipse happen right here in Hamilton and other parts of southern Ontario. And I cannot emphasize enough how much you want to see this, all right? And having the opportunity to see an eclipse like this is it is one of the most beautiful and spectacular phenomena in nature that you can observe. And all of those things that we've been talking about, seeing the chromosphere, seeing the prominences, seeing the corona, it's all there right in front of you, and so easy to see. Partial phases like this one, and total phases when you can see the corona. Now, this here actually shows the corona at different eclipses that occurred at different times in that 11-year solar cycle of active and quiet, active and quiet. When we get this eclipse next year, some 15 months from now, we're going to get it during a very active time of the sun's cycle. And you can see how the corona changes. During quiet times, the corona tends to be very streaky and very directional. But during active times, the corona tends to shoot out in all directions. And that's this one up in the top left is the kind of thing that we can expect to see in the eclipse next year. That's coming a year from April. All right. And is that it? Well, yes, it is. When this thing comes, when this eclipse comes a year and a bit from now, I don't know what the club is planning to do, but this is something not to be missed, and I can't encourage it enough. And when it does happen, you'll be able to look at these things and perhaps think back about a little bit with some little bit of understanding about what is going on that sun that you're looking at. And that's it. Thanks very much.
Are there any questions for John? Brett has the microphone, and he'll come to you, and so the Zoom people can hear you.
Thank you so much for the amazing presentation. Really, it was very informative. I do have a question. Actually, I have two. The first is I wanted to understand how is it that the scientists get to know what's inside the sun and basically all the information that you provided. And the second question is I kind of wanted to understand what is being planned for the solar flares that may potentially can occur during the next whatever years in the future.
So both of those are really, really excellent questions. That's all well and good, but how do you know is always a question that we should be asking in this field and any other science, right? Solar astronomy is something that has been built up over a long, long time. And over this past century, the 20th century, has taken leaps and bounds. Our understanding of, it had to wait until our understanding of nuclear physics. And that didn't come about until the first half of the 20th century. Prior to that, we had absolutely no clue what was going on inside the sun and what the source of energy could be. We did understand that by compressing gases, you can produce heat, and we could understand that the tremendous gravity of the sun could compress gas enough to produce that kind of heat and energy, but it would only be able to do that for so long before the energy was spent, nowhere near the lifetime of the sun, and that left astronomers puzzled. But once we had an understanding of nuclear physics, right, once we understood how the atom worked and how energy was exchanged between atoms, and once we understand the processes of nuclear fission and nuclear fusion, the answers presented themselves, all right? Now, the truth is, all right, that some of our understanding of the interior of the sun, it remains elusive and remains mysterious. There are some things that go on in there that we do not have a truly comprehensive understanding on. And it's very possible that what I've described here today, I've left out like numbers about how big the core is and the transition zone, convection zone, and so on and so on. We could be off on some of those. That's very true. That's very true. But once we had that understanding of nuclear physics, the answers presented themselves. It was an aha moment. It's like, oh, this is what's going on in the sun. As far as how the solar environment can affect us here on the Earth and what we're doing to protect ourselves from that, that's also an excellent question. We have certainly felt the effects of it in the past. All right, there has over history, technology has always been susceptible to disturbances from the sun, especially, again, in the past 100 years when we've become so technology reliant, right? As recently as, was it 1989, was that widespread power outage that we ended up attributing that directly to coronal mass ejection from the sun that poured tremendous number of charged particles out, were funneled by the Earth's magnetic field here down to the surface, interacted, it overloaded the power grid, caused a cascading effect, and a wide number of people experienced a power outage. Most, first world countries have have facilities in place to withstand that kind of thing now. We hope that we've learned lessons from how the power grid can suffer widespread failure through a cascade effect. But the fact remains that we're even more reliant on technology today, including satellites up there, which are very susceptible to solar interference. And I won't kid you, it's entirely possible that a coronal mass ejection or solar flare could knock out key satellites that we rely on for communication and things like that. That could still happen, absolutely.
Chinese had ancient records of sunspots, but has much been done to see if they can trace the 11-year cycle with those sunspot records?
Oh, so that's a terrific question. I don't know the answer to that, but I'm going to say that I would suspect so, because although I don't know the answer specifically in this case, I do know that we have been able to look back many, many, many hundreds of years, and we've been able to find we have found that all the evidence we have supports the idea that the 11-year cycle has been going on all of that time. But I don't know how thorough they are and if it's enough to really trace out that 11-year cycle. I'm sorry, I honestly don't know more than that. So.
What's the basic science that says it is hydrogen?
The basic science that says it's hydrogen? Okay, so for that, we use something called spectroscopy. Every element, hydrogen, helium, lithium, beryllium, boron, carbon. Anybody know the Elements song, right? Every element, okay, as it absorbs energy and releases energy, it releases that energy at a very, very specific set of frequencies, all right? And we perceive frequencies as color across the electromagnetic spectrum, not just the visible colors that we see, but off into infrared and radio, into ultraviolet, X-ray, gamma rays, and so on, right? And each element releases energy at very specific frequencies. It has its own unique pattern, its own unique fingerprint. If we get energy out of hydrogen in a lab, it creates that specific pattern every single time. If we do it with helium, it creates another pattern every single time. We then look at the light coming from the sun, and we look at the frequencies it's coming in. And it's this tremendous hodgepodge of lines. But then you get to play detective and separate all the patterns out of that and see how many patterns you can create. And the patterns for hydrogen, carbon, oxygen, and other elements all show up. But the vast, vast majority is obviously tied up in the hydrogen. When they initially did this and found looked at the spectrum for the spectrum for the sun, they were able to identify all of these different elements except one mystery element that had not been observed in the lab before, and that's the one that, as I mentioned, they named after Helios, and they called it helium. It was discovered on the sun first using spectroscopy. So that's how it's done. And we use spectroscopy and other things. That's how we know what the atmosphere in Jupiter is made of. And we can use it as we look at other stars, and we can see the composition of other stars, all by looking at the specific frequency of light that comes from them. Matthew, you want to add on to this? Yes, I did. So, thank you. Yeah, so at the very back, Doug is holding it up at the back right there. There is a spectrum of the star Vega that Mike Jefferson created, and he was a skilled amateur spectroscopist, and there it is. And you can see in the light there, you can see the lines showing up. And these are the emission lines coming from, the absorption lines coming from Vega, another star. Ta-da! So there's a wonderful example. That's the method right there. We do it with the sun, and we get a very complex and detailed set of lines in the spectrum, and those lines are representative of the specific patterns that we get from each specific element. So we look and we say, is there any of this element there? Nope, that pattern's missing. How about this element? Yes, there it is. And in the end, those are our clues right there that tell us exactly what gases are in the sun. And of course, we now know it's about 3/4 hydrogen, 1/4 helium, and traces of other elements like carbon and oxygen and things like that. But 3/4 hydrogen, 1/4 helium. So excellent question. That's a good one. Yeah, I liked that a lot. Okay, so, Reed, yeah, Reed.
What is known about the mechanism that drives the 11-year solar cycle? And does that have anything to do with the tenuous balance between gravity and heat pressure?
Yeah, so it turns out, I mentioned how, that's excellent. I mentioned how stable our sun is and how unstable some other stars are. But our sun isn't completely stable, is it? It's not. Our sun is a variable star. Fortunately for us, it varies a very small amount. So we're certainly able to withstand that. We see other stars that go through drastic changes over time. And different kinds of variable stars, they can change over a period of days, weeks, months, or years. Our sun goes through this very, very slight variation in energy output over a period of time, but fortunately it's so mild we're able to endure it easily. Yeah, easily. Now, the truth is, though, that there's other things about the 11-year cycle that we don't know. And I'm always very happy to stand up in front of people and say, we don't know everything about this topic, because that means that there is still some mystery out there and discoveries waiting to be made. And we don't, even though it's sitting right on our doorstep, it's the star on our doorstep, there's still more to be learned about it, about the interior workings, about the 11-year cycle. There have been times when the 11-year cycle, there was one time a few hundred years ago when the 11-year cycle just stopped. And it stopped for several decades. And the effects here on Earth were very strong, actually. It caused quite a strong climactic change here on the Earth. And then the cycle started up again. And we have no idea why that happened. and if it might happen again at some point. We have no idea. So yeah, so anybody remember what years that was? 1600s, yeah. I don't remember the years, but yeah. So yeah.
Matt, can you start again, please? Because the Zoom people can't hear you without the mic. Sorry.
I just remember that reading that in Boston, people were skating in the harbor in June and July during that lull.
Yeah.
People starved.
Yeah, exactly. Yeah, it was devastating when the cycle just stopped, and we do not know why it just stopped and why it restarted, but it skipped over several cycles, and it was just devastating here on the earth, just devastating. Okay, so yeah.
Hang on, Joanne.
Quick question, John. Thank you so much. How do we know how ancient solar astronomers were looking at the sun?
Oh, right. So excellent question. Like this, basically, in this photo right here. This is, and now I absolutely 100% do not recommend this, okay? There can be very large, dramatic sunspots on the sun, and when the sun's high in the sky at noon, you will not see them because the sun is so dazzlingly bright. Sunspots are dazzlingly bright. It's just that when we take a photo of the sun, we expose for the surface, which means since the sunspots are just a little cooler than the surface and a little dimmer, they end up underexposed in the photos and they look very dark. But they're not dark, they're still quite bright. But there are times when the sun, rising or setting, like in this image right here, okay, presents a surface to us that allows us to look at it directly. Now, I don't recommend this because it's a little risky, because there are times when the sun could be setting like this and you could say, oh, look at that beautiful sunset, I can stare right at it, but it might be just over the threshold where it could do a little damage to your eyes. So don't, okay, even if you think you're good, don't take that risk. But in ancient times, when people did not have the understanding of eye safety and that regarding the sun, they'd go ahead and look at times like this. And there are times when there are sunspots on the sun that are so large, especially during solar maximum, that you can easily see them with the unaided eye at times like sunrise and sunset when you can look directly at the sun. So these kinds of sunspots that they observed back then were obviously large enough to be seen with the unaided eye. Yeah, really amazing.
We're going to go, I know we have one more question in the room, right? Yes? Yeah.
Like, is it the buildup of helium, or is it a lack of hydrogen? What's going to kill it?
Oh, well, the sun?
Yeah, what's going to make it die?
So the sun spends the vast majority of time as what's called a main sequence star, and that's as it's converting hydrogen into helium. But think about in the core of the sun, over those billions of years, hydrogen is turned into helium, which means more and more helium builds up in the core of the sun. Since helium is denser than hydrogen, it falls into the core, and you end up with helium ash, it's referred to, building up in the core of the sun. And the more of it that builds up, the more of the core is filled with helium, more and more with helium, until eventually the helium fills the entire inner part of the sun that's hot enough to convert hydrogen into helium. And the hydrogen that could be converted into helium is pushed out, so far out, pushed out of the core of the sun where it isn't hot enough, all right, the gas isn't compressed enough to be hot enough to convert for fusion to take place and convert into helium anymore. So, and when that happens, the fusion process, the fusion reaction stops, the energy output from the sun stops, and that triggers a series of events that sends the sun on a different path that eventually leads to the demise of the sun. So the short answer is, eventually so much helium ash builds up in the core that it can't fuse hydrogen anymore. in the hot interior. Ooh, she went all.
Hello, Zoom.
Hello, Zoom.
Any questions there?
Any there?
Yes, we have one. We have a question from Bernie. Can you hear me?
It is off. Then what is not on?
Always amazed at. And sometimes we think the sun just gets in the way. Oh God, it's up too late. I'm gonna be observing not till midnight. And we think about that, but it gives us life, and his passion and his knowledge. I really appreciated you sharing that with us tonight. Thank you so much. So just give me 1 second and I'm going to switch slideshows. Yeah, I have no mouse. It's not moving here. Okay, so when John and I first spoke this week about how we were going to fill in for Bernie tonight, we weren't quite sure just how long everything was going to go. So I contacted some of my friends in the Blue Water Astronomical Society in Owen Sound, and I emailed Frank Williams, who has been doing quizzes for their monthly meetings. And I said, Frank, can you please share your quiz with me? Because we don't know if we're going to need time or not. We definitely do not have time for all of the questions, but I'm thinking maybe we do 3 questions from the quiz just to have a little bit of fun, and then we'll take a break. Is everybody okay with that? Douglas. Okay, Anne, if you can hear me out in Zoom land, someone has turned the chat off, and because you are host tonight, you have the ability to go in and turn that back on. So you should see an icon in the bottom of your screen for chat, and if not, you're going to go over to where the dots are and more, and you're going to find in there to be able to turn the chat on. because what I was going to do is going to ask the Zoom participants in the chat to type in, it's all multiple choice, so you don't have to make up the answers, okay? It's all multiple choice, to just type in an A, B, C, or D, and the chat is back on, Doug. So Zoom participants, please do that. And I think we will have Doug just call out what the answers seem to be from the back instead of trying to do the microphone, because that's obviously not working. So here we go. And a special thank you to Frank for sharing this with me. I really, really appreciated that. So if you want more details about the answers, I may not have them because I didn't make the quiz. So here we go. All right. Name the largest moon in the solar system. You guys can just call out in the room what you think it is. I have an A. I have a B. Do I have a Zoom answer? Zoom's consensus is B. All right, let's see what it is. And it is B. Congratulations to all of those who picked B. All right, question number 2. This is a question about Mars. The atmosphere of Mars is a lot thinner than on Earth and is made up of 2.8% nitrogen, 2% argon, less than 1% oxygen, and 95% of which other gas? I hear lots of A's. Are you sure? A? A? Are you sure? Doug, what have we got? Oh, all right. Let's see what happens. There you go. Congratulations, all you A people out there. Number 3. Which was the most intense geomagnetic event in recorded history? And this goes right back to what John was talking about. I'm hearing a lot of D's out there. Zoom, what have you got for me? I don't know if Godzilla is like a choice here, but it would be a really good choice, actually. All right, let's see what it is. We're thinking D. All right, let's see. Yeah, that was exactly what John was talking about, and that amazes me because the actual, like, the telegraph wires caught on fire, which just blows my mind that the wires would catch on fire because of the activity coming here from the sun. So when you ask the question about what precautions are we taking, that's a really great question to ask, because obviously they weren't prepared and didn't know that this could possibly happen. And when we think about how interconnected our technology is and how much of it is out in space, we can have fires on telegraph wires. Do you want to do 2 more? We'll do 5. All right, we seem to be having fun with this. Here we go. All right, observatories. You have to match the following. So I'm going to start with the first one, and you have choices to pick one. So the first one at the top. So the one that's right up there. All right, which one do we think? Oh! Okay, don't do that, Sue. All right. All right, so the answer is Newton. I pressed the wrong button. All right. Number 2, I'm not going to press any button this time. Number 2, the observatory that looks like it is a church in the shape of a cross. What do we think? Any guess from Zoom? Oh, okay. All right. So what's our guess? Okay, here we go. Ooh, very good. All right. Number 3. I'm hearing a lot of Herschel. Doug? Okay, here we go. It is the Herschel. Number 4. I'm hearing an awful lot of Dunlop. Anything from Zoom? Okay. Yay. And so the last one has to be Burr Castle. I actually had to look up how to say Burr because I wasn't sure. Sometimes these Celtic names can be pronounced in interesting ways, like my last name. So I had to look it up. But it's pronounced Burr Castle. All right, and our last question tonight. Name this summer object. I can hear the wheels turning. I hear B, E. Doug from Zoom? Zoom says E. Let's find out. And E is correct. So, thank you, everybody. Hopefully you had a little fun with our quiz questions, and a special thank to Frank Williams for letting us use those questions tonight. We're going to take a 10-minute break, and then we'll come back with Steve and the Sky This Month. Hello, everybody. Our 10 minutes is bled into 15 minutes, so it's nice to have that time to chat, but if we can all come and take our seats again, please, we'll get started with our second part. Okay, I think everybody's close to being settled again. And I always love break time because the conversations are so rich and everybody just wants to keep talking. Before I go on, I want to thank Brett for wandering around tonight with the man on the street with the microphone. It helps with our Zoom friends so that they can hear. And we've discussed the issue with the microphone, and it worked perfectly before we started, and we have no clue what happened. So we're going to have to do some thinking about that one. So welcome back to the second half. And before I continue, I forgot to talk about this earlier, but John just reminded me. For those club members who went to Michael Jefferson's funeral, the family created a little bag with a sunstone and a moonstone in it in memory of Mike. And the family had extra, and they gave them to John to bring here tonight, so that if you would like, on your way out the door, the box will be on the back table where the greeters are. You can pick up a bag of a sunstone and a moonstone in memory of Michael Jefferson, who was a very integral part of this club for a very, very long time, and a good friend. Okay. On to lighter things. All right, we have 3 door prizes tonight. 2 of them come from Michael Jefferson's library, and the middle one is it's a redonation. So Doug and I won the middle book about the moon as a door prize here, and we are bringing it back to have someone else share the love for that book. So they are up here at the front, And I'm going to ask Ed to come up tonight, and he's going to draw our first winner. Our first winner is Mr. Jim Wolseley. I'm not sure I believe that. The Galaxy book and the Astronomy Handbook are from Mike's library. Our next winner is Joanne Selchi. Yes, way. And our last winner tonight is Donna Miller. There you go. Well, congratulations. You are very welcome. You're on a winning streak. You did win the last time, and you guys won the telescope at Christmas too. That's right, I remember. That's 3. All right. We are going, I'm going to turn the mic over to Steve, who's going to come up and talk about the sky this month.
Thank you. Can everyone hear me? Yes, they can. Okay. So last month's Armchair Astronomer Challenge was to see Mercury. Oh, what happened? Did I touch something?
Yeah, hang on, give me 1 second. Sorry, everybody.
Okay, so last month's Armchair Astronomer Challenge was to see Mercury, and we had pretty consistent clouds since Christmas, I think. So just in case you wanted to see, what we were reminded of was that Mercury and Venus would be so close together on the 28th of December that seeing Venus, which is very bright, would automatically help you find Mercury. So it isn't going to get any easier than that, and it won't be in the future. But we carry on. So at the end of the month, well, let's just say in about a week, Mercury will be a morning object. And if you can get yourself up 45 minutes before the sun comes up, you'll see Mercury and Antares not far apart, and basically no other bright stars in the area. So look southeast, and then you'll be able to mark off that you found Mercury. Not quite so easily. That's even more challenge. But that's not your armchair challenge. So the other thing we were talking about last month was the moonrise. And Joanne sent me a couple of photos. She managed to snag the moon between clouds on a lucky shot the day after full moon. And her son, alerted to the need, took this excellent picture of the moon setting on the day that it was full from Alberta. I'm not sure exactly where in Alberta. Is it near Banff? Poor guy has to live near Banff. Anyway, as the case may be, he helped us out. As you had this great talk about the sun, fact is that the sun's activity is rising, and right now it's very active. And I got this useful stuff. You don't have to read any of the words. We'll get it zoomed in at the right time. From Matthew, who watches the net for me, and anyone else who wants to send me interesting stuff they see about the sky or anything that's going on, send it to me, and I'll appreciate it. And so, in fact, this shot here shows 5 different solar flares over the period of a few hours. You can see it's from basically 1759 to like 1945. So that's basically 2 hours. And the other interesting thing you can see in this picture is that so this is a 4-second annoying GIF, but when it resets, you can see that the sun is actually rotating in those 2 hours. It is actually rotating a visible amount. And so those 5 different flares, some of them very bright, didn't actually send us any, how shall we say, debris, but you can see what was going on there, rewarding all the solar observers. And this is probably one of our satellites took this. Is that from SOHO? The SDO. I'm not sure where that is. Is that between the Earth and the sun, or is it at 60 degrees? Okay. Well, as John was saying, we don't know everything about the sun, and in this case, we're just going to appreciate the picture. But yeah, the sun's definitely a lot more than just a uniform ball of gas. A good day. So this is winter, and I wanted to call your attention to Orion, which is basically the easiest to find constellation that we've got in our skies. It has a lot of bright stars in it. I think everybody here has seen Orion's belt, those 3 similar brightness, evenly spaced stars, and it's easy to find the rest of Orion. So this picture I picked because it has the names of all the stars, and really the only 2 stars you really need to remember are Rigel in the bottom right and Betelgeuse in the upper left. They're the brightest stars and the most interesting ones. But in fact, every one of those stars is like between 10 and 30 times heavier than the sun, and between 10,000 and 500,000 times brighter than the sun. And the picture that I'd love to show you that I don't have is when a star is really, really bright, it's because it's really, really hot or really, really big. So Betelgeuse is not so hot, but really big. But the rest of the stars, especially the ones in Orion's belt, are really, really hot. And so they look bright to us, but in fact, there's way more light coming out of them in the ultraviolet. And that's what's lighting up all these nebula. Those stars are really bright in the ultraviolet. And that's the same picture rendered by a different viewer. Shows the sizes of the stars, but no words. So I picked this off of Wikipedia, and I just wanted to show it to you. I called it the Orion's Belt Howler. And if you read that carefully, you'll see that they named the 3 stars in Orion's Belt. And it's about halfway through that paragraph. Alnitak, Alnilam, and Norbert. So anybody can edit Wikipedia. And so the machine that I use is called DuckDuckGo. It's a search engine, and it will preview some of your search results and show you on the side, so you don't have to click on it, which like sort of their idea of the best hit. And so this is what DuckDuckGo showed me when I Googled Orion's Belt. When you actually go to the Wikipedia article, it's been fixed. You can see here, they do actually call it Mintaka, which is the, let's see if this, there it is. Mintaka is the name of the star on the right of Orion's Belt. So you can remember them. They're almost in alphabetical order. So Mintaka is the last one, but the first two are swapped. So Al-Nilam is actually in the middle, but it's the first in alphabetical order. So if you ever have a quiz, like one of our trivia quizzes, you'll know the order of the belt stars is not quite alphabetical. Anyway, moving right along. So Orion, so easy to find, helps you find other things, especially Sirius, Aldebaran, which is like the eye of the bull in Taurus, Procyon, which is one of the very bright stars in the little dog, Canis Minor. And of course, it sends you up towards Gemini, Castor, and Pollux, which is easy enough to find as it is because it's part of the winter hexagon. So I just wanted you to know that, and I use the Big Dipper as well for pointer stars for different things. Orion's very useful in that regard. And if you keep going past Aldebaran, you get to the Pleiades, which is another interesting telescope and binocular object. So here's a chart showing the bright stars of Orion with their names and their light year distances. You can see that Al-Nilam in the middle of the belt is actually the farthest star. It's way, way brighter than the other stars, but it's far away. So they all look roughly even. Safe, that's the Meissa. That's the head of Orion. If we go back and cheat here, we can see there the chart. So there's Meissa, the one of the stars that's like the head of the putative figure here with his arm and his shield. And it's really, I got to give them credit for coming up with a story for this thing because it's a really good match to their, you got your hunter, you got his club, he's got like a bull to fight, the whole sky is just, it's like they set it up. Anyhow, moving right along, there's a lot of interesting trivia on Orion, and you really only have to remember two words: 9 planets and Orion constellation. And there was far too much there to include in my talk, but I highly recommend just visit that URL and have a nice read of all the stuff. But there's a couple things left to go. I wish I had a pizza, but I don't have a pizza here. I need a flat object. Let's see. Here, a book. So I want you to think of this book as like a plane. In fact, the equatorial plane of the Earth. And we know that when the Earth orbits the sun, that if the Earth's orbit was, say, in the plane of this room, like parallel to the floor, the Earth is tilted about 23 degrees. So it rotates, but its equator, its equatorial plane, stays in the same place all year long for years and years at a time. Now, actually, though, if you go for 23,000 years, the Earth's equatorial plane is actually precessing like this. So where we are in Canada, roughly 45 degrees up the Earth, there's like a cone below the Earth centered on the South Pole. We can't see any of the stars that are down there from here. They're perpetually below the horizon. But as the Earth precesses, that cone, which points over there, will eventually point over here. And more of the stars that we couldn't see will become visible. Just wait like a while. And so this is not your armchair challenge, but I wanted you to know that as the Earth precesses, the Orion will eventually become very, very hard to see. So we're actually very lucky this month and this multi 10,000 years that we have Orion prominent in the sky. It's got a zillion interesting things to see with binoculars, with a telescope, just with your naked eye, just using it to find other things. So take a good look at Orion. It will definitely repay you. So here, this particular article was centered on Britain, but yeah, it'll be pretty low for us too. in just 12,000 years from now. But so don't delay. So now I like to print these out because it makes it very easy for anyone to make a quick note. You don't have to go to the website. The moonrise this month, let's just say after this meeting, February 5th, will be at this angle, 62.24 degrees. That's the number to remember. That's where you're going to be looking for the moon, no matter where you are, assuming that you go to Dundurn or just out your apartment window or over to Hutch's by the lake. It's still roughly 62.24 degrees. And there's the time too, 5:27 p.m. So I'm not saying that I'll be there, and we haven't had cloud-free moonrises for quite some time. But we keep giving it a try, and pure luck will deliver eventually. So this month's armchair astronomer's item is something you definitely don't want to miss. It's the Naked Eye Comet C 2022 E3 ZTF, which stands for basically the satellite that found it. It's in the sky now. It's near Hercules. This is tonight, January 13th, roughly 20 minutes from now. And this is a star chart showing the area there. And here's a zoom in. But it actually, like if you've got binoculars and it wasn't cloudy, which it is, you'll see it. And it's not moving very fast. So I did the math. It's basically just going to be here. So it's moving very slow, just like a degree per day. So any chart, even the stale one, is going to help you find it. And it's right there. And I got a picture of it. Not this picture, though. This picture shows, I wonder if I can zoom that out. Okay, so this picture shows the other comets that are in the sky. I'm telling you that an 8th magnitude comet is really hard to see, even in dark skies. And they say, oh yeah, sure, we'll list these comets, but this is your man here. This is our comet. And so the way to read one of these charts, though, this comes from heavens above, is to look at the constellation it's in. And you know whether you can see Cassiopeia. It's not like you want to mess around with like what time of day it is right now, whether it's at 20 degrees. Like when I did this, it was in the afternoon. But if it's in Cassiopeia, then maybe it's worth a look, but you'd have to live in like Utah or have like a 16-inch scope to see a 10th magnitude comet. So this is the 4th comet on the list. It's not I call it the lazy comet. So I didn't print the picture of its orbit, but Comet 29P, that's a periodic comet, Schwarzmann-Wachmann. It's at 10th magnitude right now in Auriga. It's right up in the middle of the sky. It's basically on the meridian at midnight. It's dim, but its orbit is almost circular. I've never seen a comet, like called a comet, that's basically, it's just outside the orbit of Jupiter for its whole orbit. It's got a 14-year orbit. Doesn't get much closer. It goes from about 6.5 AU to 7.5 AU, but somehow it's an active comet. So that I found very interesting. Okay, so this is where that impossible to see comet is. I mean, I think I'm being realistic here. I've looked for 8th magnitude comets with the Great White Scope at Starfest and not. I had to struggle. I don't recommend giving it a go. But it's up there. And okay, so that's visual. If you have photographic equipment, you could probably catch it. But you'd have to do like a time exposure. Okay, so I wanted to show you this book. I talked about carbon stars last time, and I actually joined the Astronomical League and ordered their the free book that comes with their membership. You can pick one of their many different booklets. And so I've got this Carbon Stars book that I mentioned, and if anyone wants to come and take a peek at it and flip through it after the meeting, you can come up here. And here's what it would normally cost, $12, and it takes roughly 4 weeks to get here. Oh, I see. Okay, so that happens to be the last slide in the show. So somewhere here, I was certain that I had a good photo of that comet. So we don't have, okay, well, there you go. Bait and switch. So definitely want to be looking for that comet. And I don't have a picture, but it does have a tail. It's not just a ball. And that's your armchair astronomer challenge object for this month. Okay? So everybody, I wish you clear skies because we certainly could use them. And that's all. Well, are there any questions? Oh, that's it.
So thank you, Steve. Always really, really interesting. And I too hope for some clear skies so that we can get away from the computer, looking at pictures there and go out and see. Just before we close tonight, if there is anyone who wants a calendar, Doug's showing them off at the back. And Matthew is looking for people who may be interested in coming and helping out on the 18th. We really do need your help because we don't have enough people on council who can handle the whole thing ourselves. So we do need some people who will be willing to bring their scopes. It's a really easy day. First time I did, I didn't know what I was doing, but it worked out just fine. So please speak to Matthew before you go tonight or send him an email, not the one, oh no, that was John's email about the Astro 101 class. Yeah, not that email, but send it to second chair. And have I forgotten any announcements? John? Okay, I'll just repeat that for Zoom people, not that they can do it. But the two spectrographs at the back, the one that I did the Vanna White thing with, there's two of them and they are free to go home. Chris, what's in the box? Don't. Okay. Don't take the solar scope in the box. It's just for looking at right now. And anything else? Going once, going twice. All right, our next meeting is here, Friday, February the 10th, and hopefully there'll be some clear skies in between. And until then, thank you for coming tonight, and everybody take care. Thank you. Thanks, Jim.